simple. You have to use a spatial measurement device. It is found that the lamp using sodium vapor, okay, it's the gas state of the sodium. Inside the bulk of that lamp exhibit two close yellow frequency, this one, right? And two yellow frequency are different by far away by this amount of wavelength, right? 589.0 and 586 nanometer. So it's the difference of the wavelength is only 0.6 nanometer, but they are different. Okay, they are not from the same energy level, and you need to use a high precision spectrometer to observe the light from these two layers. Okay, it's beyond the scope or the ability of our human eyes to detect these the difference of wavelength from the yellow light. By using high resolution spectrometers, we found that the yellow light emits two wavelengths. The first one 589, this one, and 589.6. Okay, a little bit greater. Okay, this one, right? Yes, the larger the wavelength, the lower the energy, right? So the energy difference here is smaller than this one, right? The two distinct frequencies are known as phi structure, but no one could give any explanation to this phenomenon. So what is the reason behind that? No one could tell. So yeah, and that's the challenge to many physicists at that time. Okay, the idea of electron spin, okay, was widely accepted as that suggested by Georg Uhlenbeck and Samuel Goudsmit. But it was actually proposed by Leif Kronich during his PhD in January 1925 at Columbia University. Okay, if you want to discover something which is which has high impact to the world, right? You may need to study PhD to do the doctoral degree, right? And only at the PhD level, okay, you could build up or discover something meaningful to the world, okay, the world of science. And that's the Leif Kronich, okay, PhD thesis that addresses the idea of electron spin, but no one would accept it at that time. Okay, only the people that have influence to the society, like Professor Georg Uhlenbeck and Samuel Goudsmit. This effect was well explained or completely explained by an Austrian physicist whose name is Wolfgang Pauli. Okay, this guy is quite important to the Society of Physics, and if you want to see who's this person, right? Wolfgang Pauli. Wolfgang Pauli, right? This guy is quite meaningful to us in atomic in quantum mechanics. Oh no, this is in German. Here. Okay, this is Wolfgang Pauli, but his full name is actually Wolfgang Ernst Pauli. Okay, he's a German, and he was this is the German word, and he's an Austrian theoretical physicist. I mean, he's from Austria, and he is the pioneer of quantum physics. Okay, and he also received the Nobel Prize, okay, because he discovered or gave the good explanation of the electron spin. But the idea was actually discussed by Cronich, but he is not well accepted because at that time he was only a PhD student. To describe atomic energy levels, Wolfgang Pauli proposed a fourth quantum number. Okay, yeah, and that quantum number is known here. Okay, you may have already seen in the standard table of elementary particles in physics. It's called a spin number. Okay, spin number could be 1/2 or negative 1/2, right? The spin number. Where is that? Yeah, we'll talk about it later. Yeah, the spin number is the last quantum number that physicists have accepted. Okay, maybe in the future there might be another new quantum number, I don't know. Okay, but at the moment there are only 4 quantum numbers, and the last one, which was just discovered on Earth, is the spin number. Okay, this effect was explained by Wolfgang Pauli to describe the difference of the splitting of the energy levels here. Okay, this fourth quantum number is called spin magnetic quantum number, or simply speaking, spin number. Okay, the full name is spin magnetic quantum number. What is the difference then? The second and the third orbital quantum number, right? It's called yeah. The second one is called orbital quantum number, and it is denoted by the letter L. And the third one is the orbital magnetic quantum number, M with the subscript L. And the last one is called spin. I need to mention again here. Okay, orbital quantum number L and orbital magnetic quantum number M with subscript L, and the fourth or the last one is spin magnetic quantum number M with subscript S. Okay, M with subscript S here, and simply speaking, we call spin number MS. Okay, the spin number MS is not only any feature in the solution of the Schrodinger's wave equation. Okay, if you go into the detail of the theory of quantum mechanics, physics would start from Schrodinger's wave equation. You may see some in the next section. You could not find the detail of spin number MS in the Schrodinger's wave equation, but it comes from the equation derived by Paul Dirac in 1927. Okay, because we are in the high school level, we could not get into the detail of many things on this. Okay, because it involves a lot of calculus. Okay. Anyway, for us in the high school level, what we could understand is the following. It seems like this is the nucleus of the atom, right? It composed of proton, neutrons. Okay, several number. It depends on how big your element is, right? In the electron is moving in this way, okay, around the nucleus of the atom, and this is the electron, right? Denote E with superscript minus, and the electron, let's say it turns around like this by using the right-hand rule. Your time direction is going to point up, and we would call, if the electron during this rotation, we would realize that it seems like electron rotate itself. It's like our Earth rotates itself, right? That's why we have daytime and nighttime. But anyway, our Earth just move around the sun, right, which is the center of the solar system. It's something like that. For the atom, we have nucleus, and electron is moving around the nucleus, but at the same time, it seems like electron is rotating around itself, but it's not true at all. Okay, the physicists just give this notation. It looks like, okay, the electron moving around itself, but it's not true at all. Okay, yeah, if the electron is rotating around itself, and the movement in this direction, according to the rectangle, we will have the thumb direction pointing up, and in this manner, the physicists call spin up. Okay, and spin up will correspond to the value of ms equal to 1/2. Okay, and that's why we have here the notation for the here the ms equal to 1/2. Okay, 1/2 for the up quark, down quark, and so on. Even the electron has the 1/2 spin number, and many elementary particles have also the spin number as 1/2. Okay, and photon has one spin number as 1. Higgs boson has no spin number at all, and so on, right? Yeah, 1/2 is the spin up quantum number, and it is also possible when the electron moving around itself, and it moves in this way. If you look from the top view, you look at it from top view, is like a clockwise direction, right? And the clockwise direction will lead to the thumb finger pointing down, and this it's known as spin down. Okay, and when the electron seems to rotate like this, okay, in the clockwise direction or the thumb direction pointing down, you have ms equal to 1 or minus 1/2, and that's the spin down electron. Okay, and the energy of the electron is slightly different for the two spin direction. Okay, during the rotation around the nucleus, electron could have two possibilities: spin up and spin down movement. And with these two difference of spin up spin convention, we have two levels of energy right here: 3/2, 3p 1/2, not 3pi, sorry, 3p. Okay, ms equal to 1/2, meaning spinning up. Ms equal to or minus 1/2, meaning spinning down. Okay, the energy of the electron is slightly different for the two spin direction. Okay, so yeah, the meaning of slight difference means the split of these two energy levels right here. Okay, and yes, the energy difference account for the sodium doublet or double energy levels, sodium double waves. This new quantum number doubles the number of allowed state from the conventional quantum state in the literature that are previously specified by 3 quantum numbers, such as N, okay, the principal quantum number, L, the orbital quantum number, and ML, the orbital magnetic quantum number. Okay, so right now at the moment we have 4 quantum numbers, right? So we need to reach 1410, right? Not sure it's 1410, 605, 1410, right? 1420, I'm sorry. So at 14 we're gonna finish, and we let M604 to get into the classroom. Okay, let's continue our story, the quantum mechanics. Let's consider a hydrogen atom. Now we will get into the detail of the configuration of the quantum numbers. Okay, now the quantum numbers are plural. Okay, not only a single number in anymore. Determine the quantum. Let's consider the hydrogen atom, right, which is the basic atom for us. Determine the number of states with a unique set of values for Lm, Lms for n equal to 2. Okay, once you have n equal to 2, right? Once you have n equal to 2, yes, L could be, what is that? L could be 3 possible cases, right? The first one, L equal to 0. Oh no, 2 cases only, I'm stupid. There will be only 2 cases, right? Because L equal to 0 and L equal to 1, right? Yeah, for L equal to 0, you could have ML equal to 0 only. And here you have ML equal to any value in that set between, what is that? It's -1, 0, and 1, right? Yeah, something like that. And MS is the possible value for the new quantum number, which is spin number, right? MS could be 2 things, 1/2 and -1/2, right? Yes, and this also valid for the case here. So you could have 1/2 and -1/2. All right. Yes. So now it's time to make the configuration of quantum numbers. So you would have a set of N, L, M, L, and MS, right? N could be 2, right? So you have 2, L is 0, M could be 0, and MS is 1/2. And another possible case is 2, 0, 0, -1/2. Okay, and anything else? Nothing more, right? But for the right hand side, once we draw it here, we could have n equal to 2, right? N equal to 2, and L is number 1, ML is -1, and you would have 1/2 for the first case. You have 2 for N, you have 1 for L, and ML, oh, sorry. ML is -1, and here the spin number is -1/2. Okay, and the next one is 2. Once the L is 1, right? So we have 0, and because L moved from -1 to 0 already, so this is the case. All right. So ML is 0 right here, and the spin number could be 1/2. For the first case, you have 2, 1, 0, and -1/2 for the second case. Okay, and because of the short, because we are running out of space, let's write down here. The next state is 2, 1, and now we move ML from 0 to number 1. So that's why we have here 1. And again, spin number could start from 1/2. And then second case is L is number 1 and MS is number 1. The spin number is -1/2, and that's all of the possibilities to the spin number configuration, right? You could have 1, 2, 3, 4, 5, 6, 7, 8 cases. Okay, for the quantum possible quantum state or possible values of quantum numbers. So that's here in total we can have 8 quantum states like this. Okay, this is the spanning of the possible value for NL, ML, and MS, and that's the quantum state, possible quantum state for n equal to 2. Okay, for the homework you can choose any n to get another type of quantum states. Okay, here let's consider a hydrogen atom. Determine the number of states with a unique set of value for L, ML, MS when n equal to 3. Okay, when n equal to 3, what is the possible quantum state to this case then? Right? What is the possible quantum number to this case? Let me turn on the lamp. I forget to close the lamp, otherwise there will be reflection from that monitor. Okay, right here you could have the quantum state like this. Okay, and for n equal to 3, let's go ahead with that. Okay, when n equal to 3, you could start like this. Okay, when n equal to 3, there will be 3 cases for L, right? L equal to 0, that's the first case. L equal to 1, that's the second case, and L equal to 2 as the third case, right? And again, ML could be minus L, 0 in L, right? So right here you could have only 0 value for ML, and right here you could have ML equal to ML equal to -1, right? And ML equal to 0, and ML equal to number 1. And here you have ML equal to -2. You have ML equal to -1. You have ML equal to 0. You have ML equal to number 1. You have ML equal to number 2. Okay, and that's the 5 cases, 5 possibilities for L equal to 2. Okay, and once you know the configuration like this, it's the case for MS, right? MS could be 1/2. MS could be -1/2. And again, here, MS could be -1/2. Oh, sorry, positive first. S is 1/2. So MS could be again -1/2. And here you have MS equal to 1/2. MS equal to -1/2. All right. MS equal to 1/2. MS equal to -1/2. All right. The whole cases, the whole thing here. MS equal to 1/2. MS equal to -1/2. MS equal to 1/2. MS equal to -1/2. MS equal to 1/2. MS equal to -1/2. ms equal to 1 by 2, ms equal to minus 1 by 2. ms equals 1 by 2, ms equal to minus 1 by 2. Okay, so let's count the possibilities to this n equal to 3 case. This is the sorry, let's use this one. The first case, the second case, the third case, the fourth case, the fifth case, the sixth case, and the seventh case, the eighth case. And here we have the number 9 case, the number 10 case, number 11 case, and the 12th case, the 13th case, the 14th case, the 15th case, the 16th case, the 17th case, the 18th, the last one. Okay, so the number of state, okay, therefore the number of possible states is, what is that? It's 18. Okay, it's 18. We have 18 possible states for the electron orbits. Okay, yeah. Let's move to the next example, next detail, right, to this lecture. The question is the electron spin realistic? Is that true? All right. Is that correct? Okay, and that's the question to this one, right? Yes. Let's consider the spinning speed of the electron, right? Spinning speed. Okay, you just take a look at the ball. If this is the sphere, right? If we represent the electron by this sphere, it looks like a ball. Okay, a football, basketball, or any type of spherical ball. And let's consider the spinning speed of the electron, which is actually the tangential speed. Okay, any rotating object that rotates around itself, this is the tangential speed, right? The speed at the surface of that ball or that object, right? Which could have the, okay, this assume we have the rotational speed, which is omega t. The rotational speed is omega, or no, not omega t. I'm sorry for that. Only omega. That's the, I don't know, angular velocity. Yeah. And the radius, let's say the radius of the electron. Oh, sorry for that. Let's say the radius of the electron is RE. Okay, RE. So the tangential speed could be found from the product or the multiplication of the angular speed times the radius of this electron, right? So you could get the tangential speed from this expression. Okay, and we are gonna see the tangential speed of this electron. Okay, that's the basic formula from the classical physics, right? Let's recall the moment of the inertia of a sphere. Okay, if you get back to material 4, material 5, you have ever heard this one, right? The moment of inertia of any geometrical shape. For example, we consider the sphere right here, which could be found from I sphere equal to 2/5 and m r square. Okay, and let's say if m is the mass of any object, and we are considering here the electron, so the mass should be the mass of the electron, and the radius of this thing should be the radius of the electron. Okay, and this is the general form or general expression for any shape of the object. Okay, and we are considering here the sphere, right, which represent electron. Okay, it's a kind of lepton. Okay, it is well known that the angular momentum of any object is the product of moment inertia and the angular velocity. So once you multiply this term to omega, okay, 2/5 mr squared to omega, you could get the angular momentum, and the angular momentum is h/by2. You have the h/, and once you solve this term, okay, for omega is omega t by re, you put you leave Vt by Re to the position, when you substitute Vt by Re to omega, you would get the value for Vt. And the tangential speed of the electron here, okay, if let's say if you are very, very small and you just stand up at the surface of the electron, you're gonna feel the speed, right, that try to move you. It's 5/4 h/ by me and re. Okay, you substitute everything, the h/ in this is the max Planck constant divided by 2π, right, the angular version. In the mass of electron is 9.1 10⁻⁻31, and radius of the electron is 2.82 10⁻⁻15. Okay, even less than the atomic size. Okay, atomic size is on the order of 10⁻⁻10, right? It's 1 angstrom, but this one is something less than, much less than 1 angstrom, 10⁻⁻15. That's the radius of electron. Okay, and once you move everything, you substitute everything to this expression and you leave it into the calculator, you're gonna get the speed, right, the tangent speed at the surface of the electron. If you stand up here at the surface of the electron, you would get the speed Vt. Okay, and the outcome is the following: the speed of the tangent of the tangential speed at the surface of the electron is emerged as 515 10⁸. Okay, and you could see 10⁸ is the same scale as the speed of the light, right? The light or any electromagnetic wave move from the Hertz-Heilig-Hertz formula 3 × 10⁸, right? That's the speed of the light or any kind of electromagnetic wave. An important note is that the electron doesn't physically spin, whereas this electron spin is a pure quantum effect that gives the electron an angular momentum as if it were physically spinning. Okay, because 513 is much greater than number 3, right? We usually know that the speed of the light is 3 × 10⁸, right? So it's not the case here. It's much greater than the speed of the light, and any object could not move faster than the light. So 513 is not a valid value, but we could get it from the derivation or from the theory, but it's not, it doesn't hold true at all, because this value is more than the speed of the light. So any object in the universe could not have the speed much greater than the light. So this doesn't hold true. This is not valid. This is invalid. So it means that the electron doesn't actually rotate around itself. Okay, this notation, this understanding is not correct at all. But what is the reason why they say the electron try to rotate itself according to this figure? According to this figure, okay, it here, spin up and spin down. So in reality, the electron doesn't rotate around itself. Okay, this is only the pseudo configuration. Actually, the electron doesn't rotate it's around itself, whether spinning up or whether spinning down. The electron doesn't physically spin. Electron spin is a pure quantum effect that gives the electron an angular momentum as if it were physically spinning. Spin is an intrinsic or the hidden form of the angular momentum, but actually the electron doesn't spin and doesn't rotate at all. The Pauli exclusion principle states that no two electrons in an atom can ever have the same set of values of the set of the quantum number in LML and MS. So what we have distributed here, the possibility like this one, okay. The set of these four numbers here is the unique location for electron, okay. Electron, the electron which are more than two, okay, more than two electrons cannot have the same set of quantum numbers here, okay, and that's called Pauli exclusion principle, okay. Pauli proposed the idea of exclusion principle. So electron could not have the same set of quantum number like this, like what we have distributed here for n equal to 3, or this one for n equal to 2. Okay, and the lecture for at the moment, okay, it should be finished right now. And M605 can leave the lecture right now because I have to leave you 20 minutes for the break, right? And see you in 50 minutes, right? You get to another subject, which is English or something like that, and we will see each other again, okay, in 50 minutes. สวัสดีครับ bye bye ครับ if you have any questions just let me know, if not then just take the break. bye bye ครับ เดี๋ยวพบกันอีก50 นาทีนะครับ Why it's so high? That's the break. Okay. Test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3. ไปเบาเสียงได้เป็นคนที่เข้าที่เป็นสิ่งOkay, let's get back to. Not sure whether you could hear me on it. S1, 2, 3 test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3. Test. Test 1, 2, 3. Test 2. 3. Test 1. เสียงออกนู่นthe Bluetooth. Okay. This is the sound. Okay, test 1. กลับมาแล้วครับ Okay, test 1, 2, 3. Let's continue the section of M604. This is the what's that? Here you arrive at the outbound principle, right? เราถึง outbound principle นะครับ 6 atomic physics in 6 here. This one. Okay. Okay, the outbound principle, this one here. Okay, outbound principle. Yes. Just once we talk about the electron orbits, right? You could start from the principle of outbound. You know, outbound is the German word which build on or build over, something like that. Out is over. Okay. Yeah, you start from 1s to 2s and to 2p, 3s. Okay. It doesn't mean that you will start all. You will have all the time number 3 here. Sometimes you may need to reach first the S, okay, the S subshell when L is equal to 0. Okay, 4s and 3d, 4p and 5s. All right, in you start again 4d, 5p, 6s, and yeah, that's until the next one, which is the F. That's the case when L is equal to 3. Okay, if you take a look at this figure, this is taken from the German book. Okay, here we have the nucleus, proton and neutron at the center of the atom, and here is the electron orbit, and is equal to 1, and is denoted by S. All right. Yes, according to the Aufbau principle, you start first from S, and then you reach to S, which is this level here, and this belongs to the case when N is equal to 2 and K L, right? This is capital L. Okay, 2S and then 2P, and so the next shell is the next orbit is 2P, and then we go to 3S. 3S is right here, and yes, 3S and then 3P, the next level of the energy orbit. Yes, 3P and then 4S. So there we reach 4S, and after 4S we go to 3D, and here 4S to 3D. All right, for this right here. After 3D we arrive at 4P. So here is 4P. After 4P, we reach 5S, and here is 5S. 5S and then 4D, right? 5S and then 4D, okay, and so on. Okay, according to the Aufbau principle, that's the energy level measured from the center of the atom, right? The Pauli general exclusion principle say that. Okay, let's get back to the standard elementary table. Here you have the standard elementary table, right? The exclusion principle by Pauli first talks about the condition for electron, right? But actually his principle can be generalized to any particle, like the one here in the elementary particle table. It works with fermions. You know fermion, right? Fermion is this part of the standard elementary table. And on the right side, you have the boson. Okay, you have boson right here. Okay, and here is the fermion. Okay, is Oligofermi. Okay, fermion comes from the surname of Oligofermi. Boson comes from the surname of Indian guy, right? Boson, right? Yeah. Pauli exclusion is valid for fermion. Okay, both violet and green portions here, and he said that in this principle, it is said that the two fermions, whether up or down quark or any type of fermion that has a spin 1/2 or 3/2, can not be in the same quantum state. Okay, here is the quantum state, right? Each layer is the quantum state, and the fermions, whether in the violet table or the green table, will not have the same quantum state, and that's the exclusion principle. That's why they say exclusion, because it should be different. Okay, the quantum state should be different for different fermions. Okay, fermion cannot stay at the same exactly point and at exactly time. Okay, that's the the condition given by Pauli. The wave function, which is psi function depending on x, y, and z and t for our particle, contains all the information that can be known about the dynamic state of that particle. Okay, all these particles could be explained by the wave function, which is psi function. Actually, the psi function, yeah, because we talk about the small particle, right? It would not, we could not tell exactly where that particle is. So the exact location of that particle might not be easily found. So the way to tell the location is only to the use of probability function, and wave function is actually the probability of finding particle in its various regions. And if the particle has a shard, the wave function can also be used to find a shard of that particle at any point in the space. And the wave function can be used for other purposes. For example, if you want to find the average position of this particle, and if you want to find the average velocity of this particle, you want to find the dynamic quantities, for example, momentum, energy, and angular momentum. Okay, and in this figure, you could see the side of the wave function, but because the psi function is a complex function. Okay, it's a complex number, complex number, right? Square root minus 1. Yeah, it's difficult to tell where the particle is, but what we could see is only the probability, but the probability in complex value. And in order to see the behavior of the complex quantity, we're going to need to look at the magnitude square. Okay, this is the magnitude square of the psi function or the wave function. Well, another way is to observe the phase between the real part and imaginary part, right? That's the phase. But for the psi function, which is the probability function, psi square, the magnitude square, it is shown here in this figure. And for the 1s, okay, when n is equal to 1, right? The principal quantum number is equal to 1, and L is equal to 0, which is denoted by S. In that orbit, we could see only the density. Okay, the more shade you look at this figure, the more probability you could find the particle around here. Okay, it doesn't mean that the particle just located exactly at this point. No. It's only the probability density function. If you see the heavy shade of the color of the blue, it means you have more probability at that point, okay, to find the particle, whatever particle you want to find. And for the 2s orbit, okay, 2s2, it means the small n, which is the principal quantum number, is when it is equal to 2, and S means the case when L is equal to 0. You get the wave function like this, the magnitude square of the wave function. At the center, close to at the center, you have higher density, and in a certain area like this. This is the 3D plot actually, but they just cut down the cross-sectional view, the front view of this one. And yes, you could see the density function like this. And for the 3s, you could have the magnitude square of the wave function like this. Okay, at the center you have, in this circle, in this ring, you have more chance to find a particle. And in the outer ring, in the second ring, you have, again, more chance to find a particle. Okay. Yes, the Schrödinger wave equation is developed by, as the name called, right? It's Erwin Schrödinger. He's a physicist from, I think, from Austria or something like that. And then he lived also in Ireland, so he got two citizenships, both Austrian and Irish, I think, In principle, we can set up a Schrödinger equation for any given physical situation. The wave functions that are solution of this equation represent various possible physical states of the system. For an electron in a hydrogen atom in the state with energy En and quantum number n, acceptable solutions. Okay, Erwin Schrödinger does not only build up the wave function, but also provides the solution to that. Okay, and the solution from the Schrödinger's wave equation is the following: acceptable solution of the Schrödinger wave equation exists only when the magnitude L of the vector angular momentum. Okay. Also, this is the vector version of the angular momentum of any particle you want to find, and L is only the magnitude, right? The magnitude of this one is equal to square root L. You know L, right? L is the orbital quantum number, right? Yes, L could be any value from 0 to n-1, and that's the range for L. The angular momentum magnitude along the z-axis can be only Lz. Okay, this is the multiplication to h slash, right? Angular momentum magnitude along the z-axis can be Lz, and Lz is equal to ml. Ml is the orbital magnetic quantum number, right? Lz, which is the magnitude of the angular momentum, could be found from the product of ml and its slash, right? That is the angular version or the reduced version of the Max Planck constant. Okay, and here you can see the magnitude of the angular momentum along the z-axis in different way. This is the positive z, right? If you look at this figure and along the z-axis only, and the magnitude is the square root 6 time h slash at that point, and here is h slash, and here is 0, and here is minus or negative h slash, and here is negative 2 h slash. All right. Here is the case when L is equal to 0, L is equal to 2. Okay. Once your orbital quantum number is equal to 2, okay, you could get something like this. And for the components of the angular momentum, this is the actual vector. Okay, the L vector, it can be projected to any point around this circle, and if you rotate, it's going to be a 3D view. Okay, and Lz is equal to h at this location, Lz is equal to 0 at this location. This is the cross-sectional view of this figure, and here is the three-dimensional picture to this one. Okay, we arrive at the last example. Consider a hydrogen atom in a state when n equal to 4. Find the expression for the largest magnitude L of angular momentum, the largest positive value Lz, and corresponding values of the quantum number L and ml. For the corresponding quantum state, for the corresponding quantum state, find the smallest angle that the angular momentum vector can make with a positive z-axis. Okay, for n is equal to 4, we can try to maximize L, right, which is the magnitude of the vector angular momentum. This one, we will take the maximization operator to 84. We get this one, okay, and L can start from 0 to 1, 2, 3, 4. But because n is equal to 4, so this one, the maximum value will be only 3. So L could be 0, 1, 2, 3. So 3 will be here. Okay. So 3, you can choose whatever, right? If L is equal to 3, you get 3 times 4 and square root 12 times S slash. S slash is the reduced version of the Planck constant, right? So you multiply it with this one, it's 10 to 34. And for the largest positive value of the angular momentum along the z-axis, it can be treated in the same way. Okay, you just try to maximize this one, but since the LZ depends on ML, right? So we have to maximize with respect to ML. And once you know the LZ is equal to ML times S slash, it's going to be square root L and L plus 1 times S slash, you get something like this. So yeah, oh sorry, you get something like this. So the maximum value is going to be the positive value, right? If you take the negative value, it's going to be not the maximum. It will not be the maximum value. So the best way is to use the positive value, which is number 3. And 3 times the H slash reduced angular momentum, you get this thing, right? This value 3.16 10 to negative 34. The angular could be found from the ratio between this one, right? Maximum of this one, maximum of this one is yes, LZ, the maximum value of the LZ is 3H bar, 3H slash, and maximum value of L is square root 12 H slash, and you could cancel each other, right? H slash and H slash, you get, of course, you have also square root 3 and square root 4. Here you have square root 3. Square root 3 can cancel square root 3. Underneath here, you get square root 3 only above, and number 2 from square root 4 will kick out. Okay, we get out of the square root and only number 2 appear. And from the cosine function, square root of 3/2 is actually the number at the angle of 30 degrees. And that's why we say theta min is 30 degrees here. Okay, and the time is over for M604. Anyone who didn't write down your name yet, just write down, and we will see each other again on Friday, I think on Friday. Okay,นะครับคนไหนมีข้อสงสัยก็โปรดถามได้นะครับสำหรับ604นะครับผมไม่ได้เสียบหูฟังนะก็จบบทที่6แล้วนะครับอะตอมิกฟิสิกส์ปีนี้ไปได้ดีครับเพราะว่าคุณให้ทำคลิปชดเชย2อันด้วยจริงๆผมก็กลับมาสอนชดเชยคุณดีๆโอเคไม่เป็นไรครับก็พบกันวันศุกร์นะครับการบ้านยังไม่สั่งเดี๋ยววันศุกร์สั่งอีกทีนะครับขึ้นบทถัดไปก็คือนิวเคลียร์ฟิสิกส์แล้วก็พาร์ติเคิลฟิสิกส์ซึ่ง605จะขึ้นวันนี้แล้วนะครับเพราะว่าเขานำคุณไป2คาบนะครับนำคุณไป2คาบโอเคบ๊ายบายครับ604สวัสดีครับ All right, is that correct? 1353, right? เดี๋ยวเราต้องจบที่เท่าไหร่ครับ1420 but yeah จบก่อนนะก็เอาไงครับจะต่อเลยไหมหรือว่ามีคนออกแล้วคนออกก็หยุดไปก่อนแล้วกันนะครับเพราะว่าเดี๋ยวสับสนกันครับเดี๋ยวขึ้นบทที่7ครั้งหน้าแล้วกันนะ604ครับบอกเลิกไปแล้ว Yes.
G. Yes. So this. Here, test 1, 2, 3. Yes. Oh, soon. Okay, it's time for M605, 605 right now. So you understand, we say we will start our new chapter, which is chapter number 7, right? It's something about nuclear and particle physics. Yes, let's get into the detail. There are 3 channels: the OBS channel, and the Streamlabs channel from the mobile phone, and the YouTube to the Zoom to channel, Zoom to YouTube channel, and yeah, and Zoom meeting, right? If you want to join Zoom. Okay, yes, we start with the first topic in this chapter, which is here, okay, nuclear physics, and the next one is going to be particle physics. Okay, we will talk about fermions and boson, right? Okay, inside the topic of nuclear physics, we will see many things like nucleus size. Okay, the nuclear physics is taken from the topic of nuclear physics is taken from book number 1 and book number 2. Okay, and yeah, the first topic in this chapter will be nuclear size and the nuclear force. Okay, and then the nucleus mass. Okay, why we have to talk about mass? Because the energy has a relation to mass too. Okay, effect mass and binding energy. Okay, this is a great topic, and is full of computation. Many examples are available here in this subtopic. And after that, we will talk about radioactivity, which is a kind of particle emission, and the emission of several particles is quite harmful to human. Okay, Yeah, radioactivity will be consisted. Oh, I forget the microphone here. Okay, the radioactivity will be the story about decay rate. Okay, we will talk about decay rate, and yeah, there will be 3 particles, right, that emit from radioactivity. The first one is alpha, the second one is beta, and the third one is gamma. Okay, alpha, beta, gamma are the main 3 fundamental particles from radioactivity. And one important thing is that human uses carbon dating, okay, to evaluate or to approximate how long an object lasts, okay, from the beginning. Okay, and that's what we also talk about or consider. Yes, the second topic of this chapter is particle physics. Actually, it's not finished yet. It's not the preparation of this topic is not finished yet in these lecture notes. And because last year we don't get into these chapters so much. Okay, we don't have enough time, so it's not necessary to talk so much on particle physics. Okay, and yeah, let's start our nuclear physics. So what is the meaning of nucleus then? What is the meaning of nucleus? Of course, the word nucleus means the core or central part of something. Okay, and round, which others are assembled. Okay, it has round shape. What is the difference between nucleus and nuclei? Okay, you may get confused once you go further into this chapter. Okay, the word nucleus and nuclei are different because nucleus is only the single form, okay, singular form, and nuclei is the plural form. Okay? Nuclei is the plural form of nucleus. Nucleus is a collection of particles called proton and neutrons. Okay, the protons are positively charged. Okay, you know that proton has a positive charge, and neutron is electrically neutral. Okay, proton has no charge; it's neither positive nor negative. Okay, it's neutral. Okay, that's why we call neutron. Okay, nucleon. What does that mean? Nucleon. Nucleon is a generic term used to refer to either a proton or neutron. Okay? It depends on what you want to use in that context. Okay, the meaning, whether it's proton or neutron, depends on the context around that sentence. Okay, in the nucleus we have A and Z, right? X is the symbol, right, of that element, and A is the mass number. Okay, A is the mass number equal to is equal to number of nucleons. Okay, the particles in the nucleus. Okay, and the next one is the Z variable, right? Or Z variable. It's the atomic number. Okay, and this number is equal to the number of a proton in the nucleus. All right. Okay. The next one is the neutron number N. Okay, it locates on the right hand side as a subscript position. The neutron number N is equal to the number of neutron which are related by N is A minus Z. Okay, you have A here. A is always greater than Z, right? And N is A minus Z. For example, 2713 aluminum has the mass number 27. So the number of particles in the nucleus is 27, and the atomic number, which is the number of proton in the nucleus, is 13. Okay, if the atomic number changes, so the alphabet here, the symbol of the element, will also change. And you could find the number of neutrons from equation number 1 easily, right? 27 minus 13 will be 14, and that's the number of neutrons available in the nucleus of this aluminum. Okay, we often omit the subscript Z because, this occasion, because the chemical symbol can always be used to determine Z. Okay, but for us in physics, sometimes we need to show. Okay, even everybody can remember, but for us in physics, we assume that we cannot remember the number of proton or the atomic number of each element. Okay, the nuclei of all atoms of a particular element must contain the same number of protons, but may contain different numbers of neutrons. Okay, it means they have somehow isotrope. You know, the word isotrope, right? Of course, the number of proton would be the same for a single element, but in a single element, the number of neutron hidden or appeared in the nucleus might be different for various elements. For isotope of carbon, include carbon 11. Okay, you know, carbon has 6 protons in the nucleus, so the remaining 5 particles will be neutrons. So carbon 11 has 5 neutrons in the nucleus, and carbon 12, which is quite standardized, right? Which is around 98.9 in nature. Carbon 12, okay, you know, carbon has 6 proton, and that's why they say, you can see here number 6 at the left subscript position, and 13 carbon 6 is around 1.1% in nature. Okay, it's not easily found, but there is. Okay, that's carbon 13. We have also carbon 14, okay, which is used in carbon dating. Okay, and in general case, the mix of several isotopes could be found on Earth, right? For example, you pick up a piece of carbon. In that piece, you may find both carbon 13 and carbon 14. So what happened? I don't understand why the people from M605 doesn't appear here. ไม่มีคนจาก M605 เลยนะครับ What happened? No one from M605. No, we start from 1420, right? So that's why I cannot see you 1420. Okay. Okay, maybe I have to talk about it again. Right. Okay, anybody from M605? I have already started our chapter, unfortunately. Is there anyone from M605? Hello. Okay. So 14:20, right, is the right time for M605 in SCI33206. So we will talk about chapter number 7, and that's about nuclear physics in particle physics. All right. Okay. In this chapter, we have several things to consider. The first one is, of course, this chapter is nuclear physics and particle physics, right? So, I have to close. Okay. Yes. The chapter 7 is something about nuclear physics and particle physics. Nuclear physics is taken from book number 1 and book number 2 in chapter 29 and 30 respectively. Yes, วชิรวิทย์มาแล้วครับก่อนครับพิมพ์มาแล้ว Okay. And in this topic, we will consider the nucleus size. Nuclear, that's the size of the nucleus. Okay. In the previous chapter, we have seen the electron orbit, right, which is the full size of the atom. But here we concentrate on the nucleus of the atom. And inside the nucleus, we will see several particles. And here we talk about the size of the nucleus. And we will talk about the nuclear force, which is the force that try to combine several particles together. And the nucleus mass, okay. So the mass and the energy will be nucleus mass will be transferable amounts to to energy. So as the formula E equal to mc squared, right? Defect mass, and this is the mass that is missing, and the binding energy, because the defect mass is converted to a binding energy. Binding energy is the energy that try to keep several types of particles to stay together in the nucleus. The next one is radioactivity. Here is the effect of several isotopes of the atoms, and we have a decay rate. Okay, we have to talk about decay rate, which is the time that the amount of that radioactive elements will remain half to the initial amount. Alpha decay is the decay of the alpha particle. We will talk about beta decay. Okay, that's the decay of beta particle, and gamma decay. Gamma decay is the decay caused by the gamma ray, and the people also consider carbon dating. Carbon dating is used in several applications. If you want to observe the ancient object, you could use the ratio between carbon in that element, okay, and then you can predict somehow the lifetime of that particle, of that object. Okay. Next one is particle physics. Okay, it's the story about elementary particle, and you could see already in the previous chapter, elementary standard model, right? Yes. Nuclear physics. What is that? So what is the meaning of nucleus? Nucleus means the core or the central part of something that's round, which others are assembled. Okay, the other objects are stacked together at the core or the center of this thing, right? What is the difference between the nucleus and nuclei? Okay, we have two words: nucleus, okay, on the left side, and the nuclei. What is the meaning? Nucleus is only the singular form, okay, while nuclei is the plural form of the nucleus. So it's the Latin word. The way to make the word to be plural is in the manner of Latin language. So I cannot do anything. Okay, nucleus is a collection of particles called proton, which are positively charged, and neutron, which are electrically neutral. Okay, nucleon is a generic term used to refer to either a proton or a neutron. Okay, you can use the word nucleon, but it's not quite often. Okay, when you say nucleon, it can also mean either proton or neutron. Okay, it depends on the context you are talking about. Okay, in the nucleus, okay, we won't talk about the electron orbits anymore because it's already addressed in the previous chapter. The nucleus of any element can be written as these, which is A, Z, and X and N, right, on the right side. A is the atomic mass. Okay. What does atomic mass? The atomic mass is the number of protons, okay, plus the number of neutrons in the nucleus. And Z at the superscript left-hand side is the number of protons appear in the nucleus. If you change Z, okay, the symbol here will be also changed, or will be also changed. And on the right side is the number of neutrons. Okay. N could be found easily. Okay, N could be found easily if you make a subtraction between A and Z. Okay, A is the number of proton plus neutron, Z is the number of protons. So once you make a subtraction of A and Z, you get the number of neutron. Okay, the mass number A is equal to the number of nucleons. Okay, any whether it's proton or neutron, doesn't matter. Okay. The atomic number Z is equal to the number of protons. Okay, atomic Z. You can find the number of proton in that element from the number Z. The neutron number is the number of neutrons. Okay, as the name suggested, which are related to each other by n equal to A minus Z. Okay, n equal to A minus Z. The bigger one minus or subtracted by the smaller number Z here. Okay, for example, 2713 aluminum has the mass number 27 and the atomic number 13. Okay, mass number 27, this is the number of both protons and neutrons. Okay, and the atomic number 13 is the number of proton appear inside the nucleus of aluminum. Okay, we often omit the subscript Z. Okay, this one on the left side, because the chemical symbol can always be used to determine Z. Yeah, if they just write down aluminum here, so you know already aluminum, and this is the fluency by chemists. Okay, because they work every day, they can be able to remember. They are able to remember the number of proton in each element. So when we say aluminum, it means the number of proton is 13, for example. Okay, the nuclei of our atom of a particular element must contain the same number of protons, but may contain different number of neutrons. What does that mean? Any element would have a single or unique value of neutron number, proton numbers, right? The Z value. Once you change the Z number, you could have different elements, and but for the same elements, when the number of neutrons changes, okay, we still have the same element, but it's a different isotope. Okay, and the meaning is different isotope. Okay, for isotope of carbon, for different isotope of carbon, we have carbon 11. Okay, you know, carbon has the number of 6 proton, so the number of neutrons will be 5, because 11 minus 6 is equal to 5. And C12(6), this is the famous and standard element. Okay, it's carbon 12 and 6, which is about 98.9 in nature. Okay, you could find carbon 12 around 98.9 in nature. And carbon 13, which is quite rare, it's only quite rare, 1.1% in nature. It's not easy to find. Carbon 14. Okay, carbon 14 is another isotope of the element of the carbon. Carbon 14 is used for carbon dating. Okay, if you wanna examine how long an object is, okay, you have to consider the ratio between the mix of carbon 14 and carbon 12. Okay, and then you would find somehow how long the object lasts. Okay, from the beginning. Okay, the hydrogen has 3 isotopes, such as okay, let's talk about the smallest element, right? Hydrogen has 3 isotopes. The first one is hydrogen 1,1. Okay, the hydrogen that has only a single proton and single nucleon. From the subsection here, you could see that the number of neutrons is 0 because 1 minus 1 is 0. So the number of neutrons in this kind of hydrogen is 0. Okay, there is no neutron at all. For a bigger hydrogen, it's called hydrogen 2,1. What does that mean? So 2 is the number of atomic mass, right? And the number 1 means the number of protons, right? Or it's called atomic number, right? Yes. Okay, the name H11 is known as hydrogen. H21 is known as deuterium. Okay, the deuterium, and 31 means tritium. Okay, third or tri or something means number 3, right? Yeah, that's the basic thing about nuclear physics. Okay, let's go ahead with that. In nuclear physics, a common unit for the length is, okay, in the atom size, we have 10⁻²⁻10, right, which is angstrom, right, as I told you. But once we don't talk about once we don't consider the electron, so the size of atom now reduces to the size of the nucleus only, because there is no electron moving around the nucleus anymore, because we don't consider that, right? For the size of the nucleus of any atom only, it's more appropriate to use the smaller scale, because the nucleus size now reduces. Okay, so from 10,000 or 100,000 times the atomic size. Yeah, the appropriate unit is femtometer. Okay, from the atomic size 10⁻⁻10, right? And here are 10⁵ times higher than or greater than the atomic size. Okay, not greater, less than. Okay, because 10⁻⁵. Okay, 1 by 100,000. Okay, the size of the electron, and that's the size of femtometer. Okay, it's not femtometer or Fermi. Okay, it's also possible. Fermi, I think. Yeah, several experimentalists reveal the most nuclei are approximately spherical. Okay. Yeah, the shape of the nucleus, not only a single nucleus, every nucleus around the world. We assume that the shape, a geometrical shape of the nuclei is spherical, and we have an average radius that is given by R equal to R0 and A times 1/3. Okay, that's the third square root. Square root 3 of A. Okay, and A, you know A, right? A is what? A is the atomic mass, right? The number of nucleons. Okay, let's. It depends on which element you are talking about. You want to consider. Okay. Yeah, R0 is the constant, and it's equal to 1.2 times 10⁻⁻15 meter. Okay, that's R0. And please know that if you have bigger elements, okay, the nucleus of that element is going to be also bigger because they just have square root of 3. Right? Since we will derive something on this page, since the volume of the sphere is 4/3 pi r with the number 3, right? The relation of number 3 will give us R0 and A, right? R0 and A. So we take the A with the power of 1/3. And we arrive at the sphere, a spherical shape times the atomic mass, right? And which means the volume is linear to the mass number of the atomic mass. Okay, it's linear to that. Okay, what is that? You just substitute equation number 3. Okay, R0 A with the power of 1/3 into this expression. You're gonna get 4/3 pi r with the power of 3 and A. So from this expression, you could see that the volume is linear to the mass number or the atomic mass number. Okay, it's not good, right? It's better if we take a look at the example to learn something, right? Yes, we have ion, right? Fe, right, which come from the ferrite or something like that. Okay, ion usually has A equal to 56 approximately, yeah, 55.845. Okay, 26 is the number of protons, okay, inside the nucleus of ion. Okay, and yeah, it's quite big element in yeah. Here is the electron alignment. Okay, you have to go to 3D6, right? In 4s2. Ferrite or iron is a transition metal. Let's talk about this example. They want to know, find the radius of iron, this element, and approximate mass and approximate density. Okay. 3 quantities: the radius, the size of the atom, the mass, approximate mass of the atom, and the approximate density of the atom, okay, of the iron nucleus, not the whole atom. All right. So let's do it. To find the radius of the iron atom, we can substitute A equal to 56 as the question suggested. Okay, A equal to 56. We substitute 56 into this expression, the volume, and even more here. A 56 and R0 is this one, right? So you get the radius of the ferrite. Okay, our ferrite will be R0A. This is to 1/3, and from this code, right? From this calculation, R0A 1/3 Okay, we just take the square root, the third square root of 56, and you multiply with this value, you get the radius in meter, and it's equal to 4.6 meter only. Okay, but 10 to negative 15, which is in the angstrom scale, right? It's even smaller than the atomic size, right? Atomic mass, what is that? Mass is the number of the product of is the atomic mass, right? The number of nucleon. So the number of nucleon times the mass of nucleon. Let's say the mass of the nucleon for ion is equal to 1.67 times 10 to negative 27, and that's the mass of the nucleon in general situation. And because physics, that's the number of nucleon, right? After you make the multiplication, you get 9.352 times 10 to negative 26 kilogram. Okay, from 5, the volume V of the ion nucleus can be computed by the following. VFE, right? From this one. Okay, here. 4/3 pi r0 to 3 and times A, which is 56. Okay, you just pi r square, right? 4/3 pi r square times 56, and you just get the result. 4.053 times 10 to negative 43. That's the size in cubic meter of the nucleus of the ion. And the density of the ion is rho Fe m, which is the mass, right? The mass we got from equation number 7, and the volume, right? The volume we have just got from this expression. Okay, 4/3 pi r0 to 3a. Okay, the density will be the ratio between the mass and the volume, right? So we get 2.3071941 times 10 to 17 kilogram per cubic meter. We get something like this. Okay, and that's the density of the ion nucleus. And so what do you think? We could see that it's 10 to 17, right? For water, we have the density on 10 to 3, right? 1,000 kilogram per cubic meter. But this one, my God, is extremely dense. Okay, 10 to 17, I don't know. 10 to 14 more dense than the water, right? It's extremely dense, and that's why metal ion is very, very strong. Okay. In a nucleus, now we arrive at the topic of nuclear force. Okay. What is the nuclear force? Okay, nuclear force is something that appears inside the nucleus. Okay, in the nucleus, the protons attract each other via the nuclear force. Okay, and at the same time, they repel each other because they are protons. They are positive. They have positive charge. Proton and proton will try to repel each other through the Coulomb force. Okay, the repelling force. Okay, the pushing force, because I am proton, you are proton, so we try to put us from each other, and that's the general sense for electric force, right? And the way to compute that force, is given by Coulomb. Okay, and it's known as Coulomb Force. Okay, nuclear force is an attractive force. Okay, that of course because there is repelling force caused by the same type of charge. Okay, and the nuclear force is the attractive force that acts between all nuclear particles. So, which kind of relation for the nuclear particles? The attractive force could happen for proton and proton. Okay, there is repelling force and proton and neutron too. Okay, the interaction are approximately the same. Okay, there are two force types in the nuclei, and that's weak nuclear force and strong nuclear forces. Okay, what does that mean? The strong nuclear force is about 100 times more attractive than the repulsive electromagnetic force. Okay, it's stronger, 100 times more attractive. Nuclear forces are short ranges. Okay, if you try to separate the particle like proton and neutron far away from each other, there will be no nuclear forces at all. And the nuclear force will fall down when the nucleons are separated by a few femtometers. Nuclear forces become extremely repulsive if the nucleon get too close. Okay, at the appropriate location, whether it's neutron or proton neutron. If those a pair, okay, if the element in these pairs is too close to each other, it's going to be extremely repulsive. Okay, pushing force. Okay, so the neutron and proton will stay in a good condition usually. And what happens if we plot the number of protons, so the bigger element actually. When the element is bigger, because the number of protons increases, right? We're gonna have bigger elements, okay, along the x-axis here. And the neutron number is shown in the y-axis, okay, because neutron number is independent. Okay, neutron number can be anything as the nature provide. And what the scientists have collected is the following. Once you start from a very small element like hydrogen, which has only single proton, okay, you could see hydrogen could have 0 or 3 neutrons, right? Yeah. Of course, once the number of protons increases, the number of neutrons should also be increasing, right? But once the element grows bigger, this is the case when the number of neutrons and protons is the same all the time, okay, in that slide, but it doesn't hold true in nature because once the nucleus is bigger because it's composed more proton, the size of the nucleus is bigger and bigger, and the repulsive force will be stronger. And in order to keep the nucleus stable, the nature has provide more neutron to the nucleus. Okay, and that's why you could see the black curve here is above the dash line. Okay, dash line is the prediction. We would assume that the number of neutron and number of protons should always be the same. Right? It's not the case in nature. The nature will provide us more neutrons, so that neutron can keep other particles inside the nucleus. Okay, and that's the meaning to this figure. Okay, it's really extremely far from the dark side when the size of electron is bigger. Another way is, okay, this is the Segrave chart. Okay, this plot is known as Segrave chart. It's taken from book number 2. This one is taken from book number 1. Yeah, this is that slide that represents n equal to z situation. Okay, the number of neutron and proton are always the same. Okay, for any situation, but it's not the case. What they found is when one say is 20, is 40, and 60, and 80. Okay, the curve is above the dash line. Okay, the atom needs, or the nucleus needs more neutron. Okay, to try to attract several particles to stay together inside the nucleus. Okay, light nuclei are more stable if they contain equal. Okay, the small nuclei are more stable if they contain equal number of proton and neutron. Okay, what we could observe from this graph, from this plot, is the following. Okay, here. Light nuclei are more stable. Okay, and let's take a look at this figure to it. There is no stable nuclei for A equal to 5 and A equal to 8. That's the spatial thing, right? A equal to 5 and A equal to 8. What is the meaning to that? So the summation of the number of proton and neutron could be 5 or 8, right? It's not the case, because the nucleus with a pair of protons and a pair of neutrons doesn't literally accept a fifth particle. Okay, you have to think about the good nuclei and the good nucleus. Example, when A is equal to 4, because you have already a pair of protons and neutrons, and yes, the new additional particle could not be included into the nucleus, okay, because they have already a pair, okay, and for the 8 too, right? And a collection of 8 neutrons split literally into 2 nuclei, okay. The pair of proton and the pair of neutrons are very, very stable. If you try to stack it to be A equal to 8, it's gonna be split it again to A equal to 4, but twice. Okay, yeah, that's the case that happens in nature. We can force it. Okay. Okay, note also that there is no stable nuclei for Z equal to 43 in Z equal to 61. 43 is known as the element of technetium. Okay, technetium. And Z equal to 61 is known as chromium. Chromium. It's not widely known, right? Heavy nuclei are more stable if N is greater than Z. Okay, the case when N is greater than Z means here, okay, it's above the dash line. Okay, so you can see that the big elements would have more neutrons than protons inside the nucleus. More neutrons are needed to keep the nucleus stable, okay, because it's going to bring the nuclear force, okay, the attractive force, because neutrons are affected only by the attractive nuclear forces, okay. But if you increase the proton, you're going to bring more the Coulomb force, okay, the pushing force by Coulomb. Okay. Eventually, when Z is equal to 83, corresponding to the bismuth, the repulsive force between proton cannot be compensated for by additional neutrons. Okay, this is the case of 83. The result that you could see in this figure are only the stable elements. Okay, we can build up the bigger element, but it's not so stable because when the nuclei or the nucleus is bigger, it's not stable. Okay, eventually when Z is equal to 83, the repulsive forces between protons cannot be compensated by additional neutron. Yeah, that's what we have already talked about. Due to the short-range nature of the nuclear force, a given nucleon interacts only with its few nearest neighbors rather than with all the nucleons inside the nucleus of neutrons. Okay. In short range, the nuclear force will take place to only the particles around it. Okay, it doesn't mean the nuclear force will cover everywhere inside the nucleus. It will act to only the nearby nucleon. Okay, nucleus mass, the proton and neutron masses are given by this value. Okay, okay, mass of proton. Of course, we know that neutron is a little bit heavier, right? It has more mass than the proton. The proton mass is 1.6726. You could see here 26 times 10 to negative 27 kilogram. And mass of neutron is 1.67492728. Okay, it starts to be bigger at this digit 49 instead of 26, and they have 29 in parentheses times 10 to negative 27. The two digits in parentheses indicate the uncertainty in the last two digits of each value. Okay. There's uncertainty of 71 and 28. I would say you may have ever seen in the previous chapter that the Werner Heisenberg uncertainty said we cannot find anything exactly in terms of location along the x-axis or the energy and time. Once we are talking about something tiny, for precise measurements, it is useful to define a new mass unit equal to 1/12 of the mass of the neutral carbon atom. Okay, let's say once the carbon 12 has full electron around that, and we measure the mass of this atom, and we got the new mass unit, which is called atomic mass. Actually, this is what you may have ever seen in the previous chapter lecture slide, right? Yes, 1U, okay, 1U, which is known as atomic mass unit. Okay, atomic mass unit is 1.6605 and blah 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 times 10 to negative 27. Okay, in the same scale as the mass of proton and neutron here. Okay, mass of proton, neutron, and electrons are the following in terms of atomic mass unit. Okay, the mass of the proton is around 1.00. Mass of neutron is around 1.0086. This is 727. Okay, and we can find the energy equivalent of 1U from the relation E equal to mc squared. Okay, you know that E equal to mc squared is the relation transformation, right? The mass energy transformation expression, right? If you start from 1.6605, that's the one atomic mass unit here, and you get the value of the the speed of the light, okay, approximately 3 times 10 to 8, okay, but it's not exactly number 3, it's 2.99, 7922, okay, and you substitute, you get the energy from the Albert-Einstein relation, and the unit of the energy is in standard way, right? It's joule. And once you convert the joule, to EV, right? Because once we are talking about EV, it's going to be more appropriate than joule, right? We just divide that number by 1.6, which is the charge value of electron. And once you convert or divide by joule, this joule, right? You get 931.491.375 EV. Okay, and once you divide it by 1 million, okay, 1 million is 10 to 6, right? 10 to 6, and after that you get 931.49. Okay, and it's for approximation, it's around 931.5 mega electron volt. Okay, this is a good number we have to memorize. Okay, 931.5. Okay, that's the energy caused by 1 atomic mass unit, right? Now, if we want to return it, many nuclear physicists often express the mass in terms of, okay, before we use the mass in kilogram, right? And for nuclear physics, it's better to express the mass, because everything is very tiny. They want to express the mass in terms of mega electron volt by c square, right? 931.5 is the mega electron volt per c square, and that's the 1 atomic mass unit. Okay, 1 atomic mass unit is equal to approximately 931.5 mega electron volt per c square. Okay, that's the unit of the mass. The total mass of a nucleus is always less than the sum of the masses of its nucleons. Okay, if you think about the number of the mass of each nucleon, whether it's neutron or proton, and you know exactly the number of nucleon in that location, and you want to if you combine them, okay, you add them, you will find that it's too big. Okay, it's a little bit bigger than the total mass of that nucleus. That we are now arrived at the defect mass and binding energy. The total energy of the total mass of a nucleus is the total energy of the Bohr system or the nucleus is less than the combined energy of separated nucleons. Okay. Yeah, if you convert the mass of the nucleus to energy, and you convert the mass of separate nucleons to the energy, you find that the energy of the actual nucleus is less than the converted energy from individual nucleon. Okay, this difference in energy is called the binding energy of the nucleus. Okay, and this is quite important for us. The binding energy can be seen as the energy that must be added to a nucleus to break it apart into its separated neutron and proton. Okay. If you want to destroy the nucleus of any element, you have to bring the energy to that nucleus. Okay, and that's the same amount as the binding energy. Okay. And then you could get the individual neutron or proton. Okay. Example number 1, exam, the first exam is taken from book number 1 in example 29.1, chapter 29 of this book, the nucleus of the deuterium. What is that deuterium? Of course, it's hydrogen, right? Deuterium is an isotope. Okay, of course, you know H11 is hydrogen. H11 is hydrogen. H12 is deuterium. Okay, H21 is deuterium, and deuterium is composed of proton and neutron, right? Yes, there is also neutron here. Okay, a single proton and single neutron staying together in the nucleus. Calculate the deuterium binding energy in mega electron volts. Okay, given the atomic mass or the mass of the deuterium nucleus plus electron is 2.14. Okay, 2.014102 atomic mass unit. Okay, so this is the question. The concept to do is the following: you need to find first defect mass, and then you convert the defect mass to binding energy by using the multiplication. Yeah. Just delta M is the delta M, which is the defect mass, okay, or the additional mass, or the losing mass. You can see it's taken from Z, right? Z times MP. MP is the mass of the proton, so Z is the number of proton. N is the number of neutron, right? And Mn is the mass of neutron minus Md. This is mass of deuterium. Okay, the mass of deuterium. You could say that there is a single proton, so mass of protons has to be multiplied by number 1. So number 1 is not written here because it's meaningless. The number of neutron is only 1, and we just take the mass of neutron 1.00866. Okay, 00866 blah blah of atomic mass unit, and yeah, you multiply it by number of neutron and minus MD. MD is the mass, the mass of deuterium, and they have said mass of deuterium is 2.014R102. And now you can make the subtraction. You can make the subtraction from 1.007 825 and 1.008665 and minus 2.014102, and you get 0.002388 U, okay, atomic mass unit. And once you get the additional mass, the mass of hydrogen is called defect mass. Okay, we can convert the excess mass to represent the binding energy hidden in the deuterium by multiplying 931.5 mega electron volt by 1 U, 1 atomic mass unit. You get 2.24. Okay, 2.224 mega electron volt, and that's the binding energy. The energy that tries to keep neutron and hydrogen, neutron and proton to stay together at the nucleus of the deuterium, the two isotopes of hydrogen. Okay, now let's talk about the atomic mass of the light element. Atomic mass Z, right? Atomic number Z, atomic mass A, mass number A, neutron number N, right? Is that we have we have hydrogen. Okay, the first hydrogen, okay, has nothing to do with excess mass and so on. But start from deuterium, from deuterium we start to have neutron, and this is the place where we start with binding energy. Okay, the next one is helium 2. Okay, helium 2 in number of neutrons is only 1. Helium 2, but when the number of neutron is 2, right? Atomic mass is different, okay, and the mass number is also different. Lithium. What about lithium? Lithium has 3 protons, 3 neutrons, and binding atomic mass is something like this, and mass number is 6. It doesn't mean that the number on the right hand side will be exactly the same or correspond to the number of proton or neutron. For example, if you arrive at this one, this is also always valid, right? The summation of the number of neutron and proton will bring you to a close value to that atomic mass. For example, 3 and 7 is going to be 13.00, blah, blah, blah. Okay. And yeah, let's move to the next one. We arrive at this example. Find the mass defect, total binding energy, and the binding energy per nucleon. Okay. The mass defect could be found from the product between number of proton, which is the atomic number, and the mass of the proton, right? And here we have the number of neutron. You have to multiply by mass of neutron, and you subtract it with the mass of carbon-12. For example, this one is 1.007825. 6 times 1.008, 6649 atomic mass unit is denoted by the letter U, right? And the next one is the mass of the carbon-12. Carbon-12 is exactly the same nucleon number is atomic mass, right? Yes, 12 atomic mass unit. And after the subtraction, you get 0.099894, and you can convert it to the binding energy, and you get 0.9894 atomic mass unit times 931.5 mega electron volt per unit, right? And you're gonna get back 92.6261 mega electron volts. Okay. The binding energy per nucleon is the average of the total binding energy, which is given by EB and A. Okay, binding energy is EB. This is what you have got in equation number 19. And because we are talking about the carbon-12 that has carbon-12 that has number of nucleons as 12, right? So you divide it by 12, you get this value, which is the binding energy per nucleon, 7.68. Okay, mega electron volt per nucleon. Okay, here is the example about defect mass and binding energy. Here we have at figure number 5. Okay, figure number 5 that talks about atomic mass number to binding energy per nucleon. Okay, that's the quantity we have just calculated. But scientist has collected all the information, to this plot here. Okay, let's make the zoom to this. Okay, binding energy, right? To start from a small one, which is hydrogen, lithium. Okay, the binding energy is increasing. Right? Binding energy increases to helium and to lithium, and after that to beryllium, to boron, to nitrogen, to for I don't know if what is that? Yes, and sodium, chlorine, and so on, right? And this is the region of the greatest binding energy per nucleon is shown by 10 band, and that corresponds to ferrite. Okay, my God. That's why the metal is strong. Okay, ferrite or iron is very strong because the binding energy of inside the nucleus of this element is the highest one. Okay, or even nickel, the binding energy is much more than typical waveform, typical element. Binding energy per nucleon versus the mass number A for nuclei that are along the line of stability. In figure 1, and here is the binding energy per nucleon as a function of mass number A for stable nuclei. This is taken from book number 2, and there is taken from the above is taken from book number 1. Okay, ED per A, binding energy per nucleon. Okay, H21 is helium-42, carbon-12, and here nickel, ferrite, and so on. Okay, now we arrive at the story about radioactivity. In 18, we have to stop at 1640, right? In 1896, Becquerel accidentally discovered that the uranium salt crystal emits an individual radiation that can darken a photographic plate. Okay, and even if the plate is covered to exclude the light. Okay, that's the accidental experiment. This spontaneous emission of radiation was soon called radioactivity. Okay, and that's the origin of radioactivity because Becquerel has uranium salt at his laboratory, and he found that there is a particle emitted from this crystal, and it can have some effect to the photographic plate. Okay, and Marie and Pierre Curie, okay, they are couples to each other, reported the discovery of 2 previously unknown elements, both of which were radioactive, such as polonium. Have you ever heard the word polonium, right? Radium, okay, are also radioactive elements. Subsequent experiments by other scientists show that other substances were also radioactive, and radioactivity was the result of the decay or disintegration of unstable nuclei. Okay, everything that comes from nuclei, once the big nucleus turns to be or changes itself to be a small one, it's gonna emit the harmful particle, which is radioactivity element. there are three types of radiation that can be emitted by radioactive structure. The first one is alpha particle, okay, and the second one is the beta particles, and the third one is gamma rays. Okay, what is the meaning of alpha particle? And you have heard alpha particle, right? In the experiment by Rutherford and so on. It's the nucleus of helium-42, right? And helium has 2 electrons, and you throw away 2 electrons, you will get only the nucleus of the helium, and that's called alpha particle. Okay. Alpha particle is the particles. Alpha particle is the particle known as helium-42 or helium-42 with the superscript 2+, this 2+ here, which means we throw away 2 electrons. Okay. Okay, alpha particle barely penetrate a sheet of paper. Okay, it cannot penetrate anything so well. Beta particles, the emitted particles are either electrons, negative, or positron. Okay, positron, right? From the standard elementary table, you could get E+. That penetrate the ability to penetrate, right? The penetration ability of beta is a few millimeter of aluminum. Okay, and for alpha particle, it's hardly penetrate the sheet of paper. And for gamma rays, this is the most harmful, in which it emits rays that are high energy photons. Okay, it's not particle, it's photons. Okay, it's boson. Okay, we could say it's boson on the right side of the standard elementary table. Okay, the ability of gamma to penetrate something is the following: it can penetrate several centimeters of lead. Okay, several centimeters, so it has a good penetration ability. Okay, and it's quite harmful to our body. Okay, and I think it's 30, right? We have 10 minutes more. The magnetic field deflects the alpha. Okay, if you don't know, if you want to differentiate these 3 particles, these 3 layers, the way to do is the following. Once you let the source of these particles like this, okay, this is the closed area. You let the particle get out of this, and it moves in this tunnel, in this hole. Okay, and once it passes, you just leave the magnetic field. Magnetic field, right? The cross symbol means the tail of the arrow. Okay, and the magnetic field is pointing toward the plane of this slide, or toward the plane of these lecture notes. Right. Yes. Because the alpha particle is a positive charge, right? The nucleus of helium-42. And once you cross your finger from the QVB, right? F is equal to QVB. Velocity vector is in this direction, and B, the magnetic of the vector of magnetic field is pointing into the plane, into this plane, right? You just cross or start from the velocity direction to that magnetic field, and your thumb direction is going to be the direction of the force. And because there is all the time force, and the alpha particle is going to be bent to the upper part like this. Okay, because there is magnetic force acting on the alpha particle all the time during this movement. Okay, for the gamma, of course, gamma is neutral. Gamma is only photon. The magnetic field could not do anything to him. So photon or gamma is going to hit the plate or the source like that without any bending. And for the beta negative means it emits electron. Okay, electron is the negative charge. When beta particle is emitted, the electron is going to receive the force, right? But in the opposite way to the alpha particle is a positive charge, but beta negative is the negative charge, so it's gonna get the force in the opposite way, and that's why you could see the beta minus beta negative has the bending shape of direction like this. Okay, and solar rays can be separated into 3 components by using a magnetic field to deflect sharp particle like that. Okay, and yes, now we arrive at the next one, which is radioactivity. One of 2,500 unknown nuclei, only 300 are stable. Okay, you can have any pair of the combination of neutrons and protons inside the nucleus of elements, but only three combination of neutron and proton are valid. It means they are stable, and we can still see it every day if you want. The remaining ones decay by emitting particles and transforming themselves into other nucleus, which may be also unstable. A nucleus is unstable if it is too big. Okay, if the nucleus contains too many nucleons, it's not gonna be stable. Okay, it will be unstable. And for the case where atomic mass is greater than 209, for the big element, you would not have also stable nucleus. If its neutron and proton is wrong, okay, when this ratio is not appropriate, the nucleus will vanish. Okay? There will be no that combination, and that's why you can't see every element that could be discovered on Earth like this. Here, this figure. Okay, you cannot find any combination of these. It will be valid only when number of neutron is bigger, is greater than the number of proton, which is above the light here. Okay, similar to atom and molecules, nuclei have internal motion. Okay, even they say they are packed together, they have also internal motion. Set up around energy level, including ground state and exciting state. Okay, and now I think the time goes by, right? We have to stop the lecture. We will continue our lecture next on Friday, right? And just นะครับก็ต้องรอ604นะครับเพราะว่า604เขาเพิ่งจบบทที่6ไปนะครับยังไม่อยากไปเยอะนะไปเยอะแล้วเดี๋ยวแบบ604จะไม่ทันนะครับ Okay, and see you on Friday. Today there is no homework at all. Okay, 605ครับ If you have any question, just let me know. If not, I'm going to capture your appearance to the group line right from Shirawit to Thanathorn, right? Shirawit to Thanathorn. M605, right? We will stop our in the right. And now this one. Stop it.